Hello, everyone, and welcome to today's webinar. Automated image analysis reduces user-to-user variability in flow cytometry gating strategies. I'm Christy Jewell of LabRoots, and I'll be your moderator for today's event. Today's educational web seminar is presented by LabRoots and brought to you by Thermo Fisher Scientific. To learn more, please visit thermofisher.com/sitepics. And please note this website is friendly and interactive. You can request a demo and ask a specialist here as well. We encourage you to participate today by submitting any questions you may have during the presentation. To do so, simply type them into the Ask a Question box and click Send. We will answer as many of your questions as we have time for at the end of the presentation. You may also submit any technical issues here as well if you have trouble hearing or seeing the presentation. I would now like to introduce today's speaker, Erin Taylor, Scientist, R&D, Protein and Cell Analysis at Thermo Fisher Scientific. Welcome, Erin. You may now begin your presentation.
Thank you for the introduction. It's a pleasure to be here. Today I'm going to be talking about automated image analysis and how it reduces user-to-user variability in flow cytometry gating strategies. My colleagues and I have been working on the Invitrogen-attuned CytPix flow cytometer, and we're going to go through image-assisted cytometry and specific features of the attuned CytPix that has enabled us to do so much work, and in addition to our normal sample processes and protocols, and a little bit about automated image analysis. Then we'll discuss sources of variance in flow cytometry data, traditional data and image parameters that can support reproducibility, and then key considerations for standardizing flow cytometry workflows. And finally, evidence of reducing variance between users with automated image analysis parameters. Let me go next slide here. So one of the really important features with the Invitrogen-attuned CytPix is that it uses acoustic-assisted hydrodynamic focusing, just like the Attune. So this means it has all the normal flow rates, up to 1,000 microliters a minute. It can be operated as a normal flow cytometer, and it's able to take bright field images at these really high flow rates because the acoustic focusing keeps the events lined up, even when you're running as fast as 1,000 microliters a minute. In this particular graphic, you can see it here at the top. This is conventional hydrodynamic focusing without the acoustic assisted feature, and these particles are moving around too much in the frame to be reliably imaged for data analysis, as opposed to down here where they're consistently maintained in a steady location. So the imaging capabilities are secondary to your standard operation. So established protocols are really unchanged, and that's what was most important for people working in our lab. We wanted to integrate this work into our existing workflows. One of the other important features of this particular technology is the software actually does most of the image analysis processing and processing. The software is able to take these large image data sets. It identifies the event within the image and outlines it, creating a mask. It IDs this object of interest on the bright fields, and uses this mask to calculate object size, object count, and over 20 morphometric parameters, which can then be used with your normal flow cytometry data. This is really, it's pretty complicated the first time you hear it, and the important thing to take away here is you don't need to be an expert in image analysis to begin using this and to use it effectively. But these parameters do enable you to understand understand cell biology and understand your samples at a whole another level of complexity. And as you learn more and use these more, become more familiar with some of the other imaging techniques that can be available if you choose to export this data and do your own additional image analysis in other software. So these automated image analysis parameters, which are calculated in the software, are split into 5 categories described here. These parameters are what describe cell morphology. Intensity features and shape features are the parameters that describe cell morphology, granularity and shape, and really give some insight into cell physiology and function. So the way that you would want to use intensity and shape features with your samples, really sample dependent, differs depending on applications. One of the most universally beneficial parameters in these automated image analysis feature is object counting, or object features for cell counting. This enables you to accurately identify your singlets, which adds a really robust way to check your manual gating and improve your accuracy. There's also system features for quality control and pixel features, just that counts pixels in the image. So cell counting is the most useful parameter for standardization and applies to almost every single sample. And then intensity and shape features are both important, but the best parameters will be sample dependent. We won't get into those too much. However, you will see count features pretty frequently in these subsequent examples. So now let's get into the biggest barrier to standardizing flow cytometry data and creating reproducible workflows, and that's variance. It's unavoidable that we work with complex biological systems, and there's going to be natural variance day to day, even within the same person, the same patient. It is impossible to control all sources of variance. However, we have identified a few ways that we can limit the variance as we acquire samples in a way that will allow us to conduct meaningful comparisons day to day between users and over time across workflows. So that is what we have been focusing on in this ways to limit variance. So what creates so much variation in cytometry data outside of the naturally occurring biological variation? And how might image-enhanced flow cytometry support these standardized workflows? I think the 4 key factors are variations due to limits of resolution, which we'll see, differences in training and experience of users, natural expected variation caused by different instruments, reagents, and different users, and finally the subjectivity that's inherent in manual gating methods. So these 4 categories are what are really limiting our ability to standardize some of our protocols and meaningfully analyze our data in a comparative way. Here's some quick examples. So this is one of my favorites, showing that scatter and fluorescent properties often fail to fully resolve populations like singlets. These brown dots here represent some aggregates that have been backdated. And you can see that no matter how experienced a cytometrist you are, if you were to come in here and manually draw a singlet gate, it would be impossible to fully include every single singlet without also including some doublets, because this boundary here is ambiguous, it's not well defined, and that's true for all of these plots. So it isn't even skill, it's simply limits of resolution with just scatter and fluorescence. Experience and training differs between users, and oftentimes there is no way to verify if a question or about ambiguous peak is right or wrong. So this is live to differential. You can see here this intermediate population could be confusing for some users. And with imaging, it's very easy to see that, oh, these cells are definitely dead, they should not be included in the slide peak. And the only peak that should be included for downstream gating is this one on the far left. So when users can gate based on data supported by images, it allows more consistent and accurate interpretations between users. And then this is the area I've been dealing with the most. When working with a very complex protocol, complex organism, this is a mouse whole lung tissue homogenate sample. When it doesn't work, why didn't it work? Is the issue with reagents? Is it a step in the process? Without a standardized method to assess my work, to meaningfully compare my data between effective sample prep and failed protocols, I really can't tell what is going wrong. And so this has been a big challenge, and what really got me most interested in finding ways to standardize my lab work. And finally, the subjectivity of manual gating methods. This is one of my favorite slides. My colleague Kevin Roberts shared this with me. She's a very experienced user, and she decided to look into the variation inherent in her own manual gating methods. She actually collected this data. See jerkats treated with camptothecin, stained with dead cell apoptosis kit, annexin 5. She drew option 1, the first population, on one day, and then came back to a new copy of the data set and drew option 2 and gated the same population. Then she overlaid the plots to look and see how close she was to her original gate. And you can see here that there is definitely a pretty significant change. Here's 49%, option 2 is 56%. And this was same person, same data set, just 2 different days. And there's already this clear variation and due to the subjectivity of having to define the boundary of a population when you're drawing manual gates. So all of these sources of variation have been holding back some of our ability to extract meaningful data about the relationships between some of the experiments and work that we've been doing, and especially that I've been doing with tissue optimization. And that is why using the image analysis parameters has been so helpful, and we're so excited to start to see how we can begin to standardize these analyses. So that's what we're going to discuss next, applying standardized techniques. Returning back to the manual gating comparisons that my colleague did, she took this a step further and tried to see if integrating an image parameter threshold would allow her to improve the consistency in analysis and reduce her own variation in analysis of these data sets across replicates. So this particular sample, or this particular experiment, was extremely well designed and minimized as much variation as I think flow cytometrists really can. All of these cells were prepared within 1 hour of each other. They were run on the same instrument. They were from the exact same stock cell source. And she kept all other settings the same. And you can see here, option 1, that was that first manual gate that she drew. Option 2, that's the other manual gate that she drew. And then this third option, diameter, is an image parameter. And what she did here is she set a diameter threshold. And for all of the data sets that she analyzed with image parameters, she used that set diameter threshold, that predefined threshold. And ultimately, comparing reproducibility, which is and using percent CV as the number of cells included in target gate across these 3 samples, she showed that there was a significant difference in the variation between the manual gated samples and her own image parameter gated samples. Ultimately, this is not necessarily reflective of real world flow cytometry samples, simply because there's no way we can control variation between our donors and sample types to this degree. But it's really promising to see that the image parameters reduce user variability and increase statistical power by doing that. And so we see this in the reduction in variation in replicates. So I ended up needing a standardized assessment method and returning back to the tissue that we've been discussing. And I had to approach it from a different angle, since variation was an inherent feature of the samples I'm working with the mouse whole lung homogenate. I needed to compare data from a series of single cell suspensions. I needed to be able to screen my final sample very quickly, accurately assess sample viability and quality in a meaningful way, which could be compared between samples, and have that comparison be meaningful enough that I could make a decision about whether or not to proceed to downstream applications like sequencing or cell sorting. And I wanted to be able to reliably identify when changes to my protocol improved sample and see those improvements in my sample preparation methods. And to do this, I assumed I would need to track over time. So I already had tissue dissociation workflows. I verified standard parameters for all sample acquisition and kept those the same for all experiments moving forward. And that was kind of the foundation of how I began building a standardized assessment for mouse whole lung homogenate tissue suspensions. And let me go next. And so here is the gating strategy that I ended up with, and we'll walk through this and the reasons why I chose these features here in just a second. So integrating analysis of images and fluorescent parameters is really important, because the fluorescent parameters do give us a lot of information, and this image-assisted flow cytometer is not meant to replace the traditional methods. And so I made sure when I was setting this up to use my typical sample assessment assays, so nuclear dye, live cytox ready flow, live dead, in addition to the image parameters, because that's ultimately what gave me this extra bit of information. And I was able to reduce this down to these 3 steps. So first, I used particle count to accurately identify singlets. The only cells that I needed counting for, or needed to count, were single healthy cells. And then this particular quadrant plot was the most time intensive to verify, because I wanted it to be a robust way to assess my sample. I used multiple sample types, multiple samples, varying degrees of quality, and I stained them with the live deads. I used nuclear dyes, some were unlicensed, and I found the most consistent location, average location for this quadrant gate, using these test samples, and again would verify them with test cases. None of the samples that I used to create this quadrant gate were then included in my actual data analysis, because I was not building a analysis workflow to fit my data. I wanted to build a tool and have my data and measure my data with my tool. So there was work that went in behind the scenes with to generate this 4-quadrant plot, and also that work really proved to me that this tool was consistent, with the different nuclear dyes, with the different sample qualities. And so I have my cytox live dead. Obviously, if it's positive, it's taking up the dye and it's dead and debris. Negative, these are the cellular events or debris that are cells that are so dead that they're not acquiring the viability dye. And because I'm also dealing with the red blood cell lysis and the fine line between lysing just enough red blood cells that they don't interfere with downstream applications, but not lysing so many that I then also lose my sensitive cell types, I knew that there would be some populations of red blood cells included in many of my samples. I did not want those red blood cells included in my final counts of healthy cells. So entropy intensity is a great parameter. It separates out dynabeads, red blood cells, those small, dark-looking, low-intensity events from the cells. And this consistently gave me this beautiful separation and isolated the population that I actually want quantitative metrics for. And so these cells are no red blood cells, no cytox positive cells, minimal debris. They are still inactive, still an inaccurate count. And we know that simply from the many live dead samples that we've assessed on site pics. The counts are always artificially high. And this has really helped illuminate for me times when I thought that my live dead and cell count totals were quite good, and then was shocked to take my sample to a downstream application, sorting or sequencing, and was shocked that I had almost no cells come back. Nothing was recovered. And now with using this technology, using these imaging, I'm able to actually confirm if these events in my total count actually are cells. And they weren't all cells, which is why I added in this extra step, circularity percent threshold. Live healthy cells in suspension are round. As they start to experience stress, become less healthy, they start to deviate from that classic round shape, so their circularity percent decreases. I felt, based on all of the optimization work I had done for this quadrant gate and looking at the thresholds in those samples of what appeared to be healthy cells, I picked 83 as my threshold for inclusion. So I'm only counting cells if they are above circularity percent threshold of 83% from this final quadrant gate. And as you can see, that's 16% of the total events run. So it's always a little disappointing to start using this and realize exactly how much of our samples can contain debris and need some extra cleanup steps. And here I have just plotted this live cell population back onto forward scatter and side scatter, so I can kind of see the distribution of likely populations, what's included in this population of healthy cells. And so once this was developed, and I felt that I kind of proved it to myself that this was effective, I have been able to use this and compare it across multiple samples. And that is where it became clear to me how important standardizing analysis is, especially for protocol optimization. I found that relationships between cause and effect are not always clear and intuitive. I believed I was making data-informed workflow optimization decisions, but the ways that I made the items that I made those decisions based on simply are not reflected in this data. So go over that a little bit more. I think a lot of those optimization, quote unquote, data-driven optimization choices were actually made on random variation. So one of the things here that I'd like to call out is what I assumed was influential and had a measurable effect on my sample quality were mechanical dissociation methods. There were two different ones I tried. My RBC lysis buffer starting temp. if I used a specific buffer after the enzyme incubation or not, and switching to a glass dish and a glass slide to help cell recovery. None of these had, there's no evidence that these had any effect. And what's even more interesting is that the times when I deviated from the protocol, which I believed to be my data-driven optimized protocol, data-informed decisions, those were the times I had the highest yield. So for the last sample, sample 5, which was of the highest yield, so we'll go back here real quick. So this sample, highest yield, I ran out of enzyme. There wasn't, someone had used most of it in the fridge and I didn't know. So I had to reduce my enzyme volume by 15 to 20%. And I expected way fewer single cells. And I actually got the highest yield of single cells. In this same sample, I also did not receive my tissue in its extra special storage buffer that we make, specifically for these protocols. And I truly believed improved viability. The lab ran out, and I expected much lower yield, much lower viability. And again, the highest yields of all those samples that you saw here. So this went against all the expectations that I believed were based on past data. And then finally, reducing the wash step at certain points. I was crunched for time, had to hurry something up. I cut out certain wash steps to just move along. I expected way more debris and potential impacts on a different ratio in live to dead cells. And I was very surprised that the ratio of debris was equivalent to most of the other samples. And this was the second best yield recovery of cells. So this definitely made me pause a bit and revisit the assumptions that I was making about how to both optimize my protocols, and really made me question how much of my assumptions and the work that I'm doing are around choices that I'm making that are just simply random, chance variation, noise in the data. And now that I have this standardized method, I'm really able to systematically approach optimizing my workflows. How do we make standardized workflows? And where should we start? Some key considerations of making these standardized workflows are that there are common practices in flow cytometry, best practices, that will prevent robust comparisons and just aren't good to standardize. So there would need to be some slight adjustments to gating strategies upstream. So first, do not overfit to one sample. And this is in gating, this is acquisition parameters. Do not overfit to one sample. And we have a tendency to optimize voltage settings, optimize plots, to make our data appear very aesthetically pleasing on acquisition and when we're viewing it. And these slight variations will actually make it so we can't compare between days and between users. So we lose that ability to extract information on meaningful relationships. So don't overfit to one sample. It's okay to have those loose gates. It's better to have the loose gates because we can then clean up some of those extra embeds using thresholds downstream. Keep all settings on the instrument consistent. Once you've identified those optimal settings, you want to make sure that your samples stay on scale. And then don't make adjustments and don't change those acquisition settings, even if you happen to be running kind of a messy or challenging looking sample, and there are opportunities to make it look better. It might look nicer, but then you probably will lose the ability to include it in analysis or comparison. And then finally, identify thresholds to use for data cleanup. This is how we compensate for drawing gates that are a little bit larger than maybe normal cytometry gates. And we'll see an example of this next. And finally, don't forget to use images to help verify accuracy of gates, your parameters, and to confirm assumptions about the identity of events within specific populations or peaks. And so the imaging is kind of critical to all this, and it is a very, very important tool to confirm and support all of these decisions in standardizing and optimizing workflows. And so as we talk about setting up the image capture gate and not overfitting, we can see here this rare population where normally someone might gate, very tightly around here. This image gate has been set very wide. This data was generated by Professor Van Egmon's lab, Amsterdam UMC. These are colorectal cancer cells spiked into healthy donor human PBMCs. The colorectal cancer cells are EpCAM positive and EGFR positive, so double positive cells. When the rare event work at such low cell counts, 1,000 events a sample, identifying every event counts. And so drawing this large gate is really important. However, that means that we now get recovery. It's 148% yield, which we know is impossible. So looking here at the image view gallery, we can see that there are a significant number of doublets, which may account for some of the double positives. Some events being counted as these CTC cells, which are double positive, but that are actually doublets. You see a lot of debris. And so the imaging supports the conclusion that this is inaccurate, which we would know. And so then this is where setting thresholds with the other imaging parameters and morphological parameters is so important and gives context to enable that accurate count. So one of the things here, using the EpCAM marker, my colleague Kevin set a threshold major diameter microns to rule out some of the smallest debris. And then also here, using circularity percent and kurtosis intensity, set another threshold, circularity above 75 with kurtosis intensity between +2 and -2. And doing this made the final cell population included in this count much more uniform. It removed the debris, it removed the doublets. So by updating her gating and adding image-derived parameters in combination with the fluorescent markers, she was able to identify events that match the expected phenotype and get a much more accurate count. And this is something that she could potentially turn into a standardized analysis workflow, standardized gate if some of these were pulled out so they weren't overfitted to this specific sample. But this is a great example of using the fluorescent parameters, the image parameters, and the image view gallery to get more accurate and image-supported results. Okay, part 3. So it's very exciting, at least for a lot of people in our lab and our collaborators, to start to see how we are being able to build in these robust analysis methods and standardize a lot of our workflows. Ultimately, we have to reduce variance in order to enable meaningful comparisons in our own work and to allow us to make those data-driven decisions. But that still does not address the issue of user-to-user variance, which is probably the most challenging part of the field and allowing certain protocols and certain experiments to be as widely reproducible as we would like. While there is a lot of anecdotal discussion and a lot of strong belief that using these image parameters would reduce variance and would enable more consistency and meaningful comparisons between users. One thing we absolutely learned using this, as you saw earlier in the process, we should not rely on our judgment to see cause and effect. So a group on site really wanted to test this and see if our observations were actually supported by data. And they looked specifically to see if image parameters controlled variance between different users. Could we make a reproducible analysis strategy? And the automated features decrease variance even when users are asked to gate samples independently. So they identified 8 users with varying backgrounds and levels of experience. This is really important because we wanted to have this variation. So we weren't just relying on users who were all trained the same way and had the exact same level of their number of years of experience. We wanted people who were newer as well. These people were asked to manually gate singlets and identify apoptotic, necrotic, and healthy jerkcats in a specific data file. This was the file that you saw earlier, which my colleague Kevin had used to identify her own variation in manual gating day to day. And then after they were asked to manually gate the singlets and identify these populations, they were given a second copy of that data set and asked to identify the same populations, but this time given instructions using image-derived parameters. And so here you can see what these gates look like. So up here in A, these are the manual gates in order to ensure that the populations that each user was working with, both with their manual strategy and their automated strategy, contained the exact same events. They were instructed to start from this process to parent gate. So that ensured that the starting population was uniform both between gating strategies and between all of the test subjects or participants. So the manual gating method here, we have 1, 2, 3 gates, all of which are subjective, meaning that the user has to make a judgment about where to place them. So lots of opportunity there for variance that can affect downstream results. Versus the image parameter gates where the users were given instructions about the size thresholds, asked to gate on singlets, and then asked to place a manual quadrant gate to separate the live, healthy, apoptotic, and dead, necrotic cells. And one of the things that was really interesting as we look at these results is that, so clearly the variance was reduced with image analysis parameters. As you can see here, purple here is manual methods and the amount of variance with these 8 users. Red is the variance after with the instructions to use the automated image parameters. But we aren't seeing a significant difference between how people are gating incorrectly. And so it looks like, here population estimated to be high, here low. There doesn't seem to be a significant trend. What I thought was most interesting is the percentage of samples that were gated for each population were pretty similar. So users were gating a similar number of cells, which leads me to wonder if the accuracy of that identification is where we would see that impact on any conclusions drawn from this data set. However, as you see here, the variation between dead, apoptotic, and live, healthy with manual methods was pretty significant. What we present CV 17.3 versus the automated methods. And so while the apoptotic cells have a pretty low variance between users, I would expect that simply because of the annexin 5 fluorescent marker providing that additional guidance as users identify populations. The opportunity here between, the variance here between live, healthy, and dead apoptotic makes me wonder what the errors were and how that might affect any kind of applications downstream if live cells were being overcounted or undercounted. But that by certain users. And again, that would come from experience. And one of the great things about this is that if we use the automated image parameters, experience becomes much less important to being able to get those accurate results. And then finally, not only were users given instructions with clear defined thresholds to enable them to analyze and interpret their data, the imaging itself just helped them confirm their assumptions about the identities of populations and provides an additional source of support and data to as they work with standardize an analysis strategy. So what we've been able to do is identify thresholds for size or intensity values and provide those to users. Users could have free reign to look at images to guide their analysis for any of the manual steps. And by giving them these thresholds, it really reduced subjective judgment required during that analysis. And so removing that opportunity for bias and the need for subjectivity really reduced a lot of that variance, as we saw. So in summary, scatter and fluorescence alone don't reduce variance day to day or between users. Reducing variation is the first step to enabling meaningful comparisons and reproducible results. Adding image parameters can reduce the number of subjective judgments that users make during analysis. And image data provides additional confirmation of any conclusions that users draw of the events in a population. So we have a lot of work ongoing with our different experiments, and I know I'm working to integrate more of this and supporting other collaborators who've been interested to incorporate some of these principles. And so I'd love to hear more questions and suggestions and your thoughts, because as flow cytometry continues on the field, we're all going to, I think, start working on this and coming up with some really great ways to integrate these methods into our work. Thank you.
Thank you, Erin, for that informative presentation. And it is now time for our live Q&A portion of our webinar. To our audience, if you have any questions you would like to ask, do so now and just simply type them into the Ask a Question box and click Submit, and we will try to answer all of your questions. So Erin, welcome back here. Let's jump into our first question that we have here. Let's start with this one. Is there anything that is different about the sample prep to analyze cells using this instrument's additional imaging capabilities?
No, that was why we were able to start testing this and just to kind of discover how useful this was for our processes. We didn't have to make any changes. The acquisition rates are identical with this instrument to the regular non-imaging attune. So unlike, I think, a lot of the other imaging cytometry technologies out there where you do have to slow down acquisition, which can affect sample quality depending on the sample type you're working with, we didn't have to make any changes. We just happened to collect the images at the same time and then go back and start reviewing them a little more. And from there, we started looking at this a little bit more closely for some of these processes.
Very good. Thank you. Our next question. Let's see. So this one has a few parts here. Is the automated image analysis available in the Attune software? If so, which version? And can we have some instruction for adding the image analysis to the standard gating procedure?
Yeah, so the regular Attune doesn't have any imaging. So unless you actually have the Attune site picks and can acquire the images, you wouldn't be able, so we have the NXT, which is the one I think that a lot of our users will be more familiar with. It's been available for quite a while. And that one is just the fluorescent, the regular fluorescence. And then the Attune CytPix collects the exact same data as the Attune NXT, but it also collects the imaging. So you would have to have the Attune CytPix. And then I'm sorry, what was the other part of the question?
The other part was, could we have some instruction for adding the image analysis to the standard gating procedure?
I'll have to double check and see where we might have those instructions available. If you have the Attune CytPix, you're able to collect the images, and then I would suggest getting in touch with your rep for further guidance that's specific to your sample types. They would probably have some really good feedback or would know who to connect with.
Thanks, Erin. And Katerina, we do have your email as well, so we're able to follow up with your question. Okay, Erin, our next question. Would a user need special training for the automated image analysis?
No, that was something that I really appreciated because I'm not a microscopist, is that you don't have to have any background in image analysis principles to start using it. You learn them as you go. And then, I've definitely myself gone in and learned a little bit more about them, and that's been helpful. But you don't have to have any special training. You just need to know to just start using it and process the images. If you have the Attune CytPix and you've updated with, I believe, the most recent software release that I think most of our customers have gotten access to through the website, we'll have to check and I'll have to make sure that I have the link. Then you should have this already installed with the most recent software version.
Thanks, Erin. Next question. Can these image parameters be exported together with the flow parameters? So in an FCS file?
Yeah, so you have the option to, even after you process the images and you're able to get these extended parameters, you will have the option of exporting the FCS with just the standard Attune NXT fluorescent parameters, or extending it and doing an extended FCS with both the fluorescent parameters in addition to the imaging parameters that you can then analyze in any software that they're compatible with.
Erin, could you elaborate on what samples and cell types that this instrument has worked with?
Yeah, so it was validated with human leukocytes, and at this point, I've seen it work very, very well with just about any standard round cells in suspension that are similar sizes. I've done a lot with tissue, and I haven't seen any major errors. And so it seems to, at this point, from what I've seen, work with most standard, more round cell types. The size range that was also validated is 5 to 20 micrometers. So if you're working in that range with, kind of your general spherical cells, I think that you're probably going to not see any issues. But one of the things that we do suggest is, always after processing your images, go and review, and we didn't go over this here, but go and review the image annotation and masking that the software is doing, and just make sure that the data is going to be reliable for your applications.
Thank you, Erin. And I think we have time for one more question here. What are the advantages of bright field imaging, in your opinion?
Well, in terms of the morphology that we're able to pick up, we're able to see a lot of the features and structures that would be a little bit more difficult to distinguish with fluorescence microscopy. And because we're using the fluorescent cytometry, we still get that fluorescent data. So this is adding a different layer to, or a second method to the analysis. We're really getting two data sets from one sample. And that's kind of how I've been thinking about it. So I do my regular fluorescent workflows, and then I confirm them with imaging. And sometimes when I combine imaging and the bright field data, the imaging data, I'm actually able to achieve even greater resolution of some sample types that I couldn't do with just fluorescence.
Very good. Erin, thank you so much for this interactive Q&A. Do you have any final comments for our audience?
I don't think so. I think we went over most of it. The only thing is definitely reach out to your sales rep, or look on the website if you have more questions. I think for sample specific questions, they would be the best sources of information. I'm not as familiar with everything located on the website.
Excellent. Well, thank you again, Erin. And I do want to thank LabRoots and our sponsor, Thermo Fisher Scientific, for sponsoring today's webinar. Before we go, I want to thank our audience for joining us today and for those interesting questions that they submitted. I want to remind our audience any questions that we didn't answer today, and additionally, those questions that are submitted during the on-demand period, they will be answered via the email address that you provided at the time of registration. And today's webcast can be viewed on demand, and LabRoots will send you an email when it's available for replay. And we encourage you to share that email with your colleagues who may have missed today's live event. That's all for now. We thank you for joining us. Thank you again, Erin, and thank you, Thermo Fisher Scientific. Have a great day, everyone.
Thanks.